Hi my dear brilliant subscribers, welcome to my channel. Today what we discuss interaction of neutrons with matter. This is continuation of Glasstone and Sesonske book, second chapter. So interaction of neutrons with matter. First we should produce the neutrons. How we can produce the neutrons? First question. The neutrons we can produce by using some atoms like beryllium 9. Beryllium 9 interacts with alpha particle and it emits one neutron and carbon 12. Beryllium 9 is the mass number, plus helium alpha particle, helium nucleus alpha particle. So helium nucleus is 2, atomic number, beryllium 4, 2 plus 4, 6, no? So carbon 12 will come. So beryllium 9 interact with the alpha particle and carbon 12, the recoil nucleus will become, recoil nucleus is carbon 12 plus 1 neutron. So beryllium 9 plus alpha particle gives rise carbon 12 and neutron. So we need to have alpha particle. Beryllium 9 is there, but beryllium 9 alone cannot produce a neutron. So we need alpha particle. Then how to produce the alpha particle? That is another doubt, no? So there are some alpha emitters. Polonium 210, radium 226, plutonium 239 and americium 241. These all are alpha emitters. Okay. Can we use these 4 as a laboratory alpha emitters? Then what is a laboratory? Laboratory means you are also working in the laboratory. It is a radioactive nuclide, it is emitting radiation. It will give dose for you. So what type of dose? You know alpha particle, it is also charged particle, and beta, gamma, that you know. Here, when this polonium, radium, plutonium, americium 241 undergo alpha decay, the nucleus, after undergoing alpha decay, it will be in excited state and emit gamma ray. The problem is whenever alpha particle is emitted, it followed by a gamma rays. Okay, most of the times. So this gamma ray energy is high, the gamma ray shielding is required. Actually, gamma ray can travel a long distance, no? What is that specific ionization called? No, not specific, range. Range of the gamma ray is highest compared with beta particle and alpha particle. So you need to have a gamma shielding. If gamma energy is high, you need to have a very big gamma shielding. So we have to choose accordingly, polonium 210 or radium 226 or plutonium 239 or americium 241. Out of these 4, which will emit alpha particle plus gamma ray, that gamma should be weak gamma. The energy of gamma ray is very less, that is most suitable to keep in the laboratory. So out of these 4, I am choosing americium 241 as a laboratory alpha emitter. The main reason is it is emitting a weak gamma that I can stop by using a very small gamma shielding material. Now alpha emitters are ready. I am taking americium 241 I am taking. Okay. Americium 241 I have, it is giving alpha particle, but ultimately I want a neutron. So neutron, where you will get? From the beryllium 9. So you have to mix americium 241 and beryllium 9 together as a source for neutron production. You understood, no? So this americium 241 plus beryllium 9 together is a neutron source. This is one of the way you are producing the neutrons. What else is there? Is there any other method to produce the neutrons? You know very well. One more thing, that is photoneutrons. Photoneutrons, the gamma ray entering into the nucleus, and it will knock out the neutron from the nucleus. For example, if you take heavy water, 1H2, if gamma ray enters into the nucleus of heavy water, if gamma energy is sufficient, it should be more than 2.2 MeV, because the binding energy of the neutron in the heavy water, it is 2.2 mega electron volt. If there is a gamma ray which can interact with the deuterium, that is 1H2, it can knock out one neutron from the deuterium. This is photoneutron. What we call it is a photoneutron. Okay. We can use this heavy water as a moderator in the reactor. So most probable in the reactor in which we are using heavy water as a moderator, these photoneutrons will be produced. Because in the nuclear reactor, the gamma rays produced by the fission product like lanthanum 140, it will emit a gamma ray energy more than 2.2 MeV. So that gamma will go to the 1H2 and it will remove one neutron from it. That is a photoneutrons. This reaction is called gamma end reaction. Means gamma is going inside, neutron is coming out. Earlier beryllium 9 plus alpha particle, alpha end reaction. Alpha is going and neutron is coming. Okay? Alpha disappeared now. Alpha interact with the beryllium and carbon 12 formed plus neutron came. That is alpha end reaction. This is gamma end reaction. Is there anything else in which neutrons will be produced? It is very easy. You can very well guess. It is fission. Fission, of course, in the fission of uranium-235 or plutonium-239, even spontaneous fission by uranium-238 also, it will emit neutrons, 2 or 3, sometimes more than 3, very rarely. So in the fission reaction also, neutrons are produced. So we can call F comma N, with fission, neutrons comes. So here reaction one is alpha end reaction, gamma end reaction, and F end reaction. F end matlab F is fission. In the fission also neutrons are coming. Okay. Now you have to think whether that neutrons are polyenergetic or monoenergetic. That also you have to think. In the alpha end reaction, means alpha interacting with beryllium, neutron is coming, that neutron is polyenergetic. Polyenergetic neutron. The neutron energy around 1 mega electron volt up to 10 mega electron volt. It is polyenergetic. If you go for that is gamma end reaction. Gamma end reaction, gamma electromagnetic wave, the energy given completely into the nucleus, the binding energy of the neutron. How much it is there, and what is the gamma energy? Suppose gamma energy is 2.2 MeV, interacting with 1H2, just neutron will come out. That neutron energy is fixed. So gamma rays are fixed energy levels. Gamma ray is coming from a particular fission product or particular any atom. The energy of the gamma ray are fixed values. The gamma ray energy will not continuously distribute. It is a unique values. So the gamma ray, suppose 4 mega electron volt is coming. This 4 mega electron volt interacting with deuterium 1H2, the neutron will come out a fixed energy. The neutron energy must be equal to gamma energy minus binding energy. That is equal to the kinetic energy of the neutron. So photoneutrons, the neutrons produced by the gamma, they are monoenergetic neutrons. Okay. Gamma end reaction, the neutrons are monoenergetic neutrons. Alpha end reaction, the neutrons are polyenergetic neutrons. Clear? What about Fn? in the fission also, the neutron energy definitely varies. The neutrons are not a fixed energy, depending on the energy shared by the fission product, and a lot of gamma ray also comes, spontaneous gamma, and some definitely the neutrons, sometimes 2 comes, sometimes 3 comes. So based on that, energy sharing will be there. The neutron produced in the fission reaction, it is a spectrum, it is a continuous spectrum from thermal region to up to 10 mega electron volt. So the fission neutrons are also polyenergetic neutrons. Alpha N reaction also polyenergetic neutrons. Only gamma N monoenergetic neutrons. Okay. Now it is clear. Now you understood how neutrons are produced. Okay. Americium 241 I told you. Americium 241 plus beryllium 9 together is a source for the neutrons. Americium, another advantage, it is half-life is around 433 years. Americium 241 half-life is 433 years. So you can use that source for a long time. And in fact, uranium 238 also produces alpha particle. But uranium 238 half-life is 10 to the power of 9 years, very huge. So the alpha particle coming, the alpha particle decay, alpha decay is very, very less. The alpha particle coming out compared to with americium 241. With the U238 it comes very less, very rarely it will comes. So better out of this all, and it should be weak gamma, it should emit, and it should emit alpha particle frequently also. Out of this 4, americium 241 is the best for alpha emitter. Okay, this is clear now. What else you can discuss other than this? Now you understood what is neutron production. Okay, alpha and gamma and fission. Okay, another thing, emission of alpha particles. How? Another topic. This is subtopics actually, the interaction of the neutrons with matter. First is neutron production. Next is emission of alpha particles. How alpha particles are emitting? That already we have. Polonium also alpha particle is coming. Plutonium also alpha particle coming because of instability. It will undergo decay. Apart from this, there are some other reactions in which alpha particle emitted. That is boron 10, B10. B10 interacting with neutron. B10 plus neutron, it will become B11. B11 is unstable. B11 emit alpha particle. Okay. So alpha particle is a 2He4. No? So what you will get? Lithium. Lithium 7 plus alpha particle will come. So this reaction is most probable if neutron is slow neutron. When neutrons are slow, this reaction probability is high. Okay. One more reaction also you can say, that is lithium. Lithium 6, Li6 also interact with the neutron. Li6 will become Li7, which is unstable. Li7 undergo alpha decay. Alpha decay plus 1H3, tritium forms. So lithium 7 equal to 2He4 plus 1H3. In this reaction also, alpha particle is produced, alpha particle is emitted. So here also the neutron energy should be small. It should be a slow neutron. So this alpha emitters, the emission of alpha particles by 2 reactions with B10 plus neutron, alpha is producing. Another is lithium 6 plus neutron, alpha particle is produced. These 2 reactions are most probable with slow neutrons only. Okay. Then what happens if neutron energy increases? If fast neutron interacting, then what particles produces? The reaction with fast neutrons we'll discuss now. Okay. The fast neutrons, some 0.1 MeV onwards, even kilo electron volt also we can call that is the fast side spectrum. Okay. So if energy of the neutron is high or fast neutron, I am calling a fast neutron, what happens? The neutron, fast neutron interacting with the particular atom, it can expel proton also. NP reactions also takes place. NP reactions. So the reactions with fast neutron NP reactions also happen. NP means neutron is going inside, proton is coming out. This is not happening with slow neutron. With fast neutron only it is happening. When fast neutrons are interacting, reaction taking place, fast neutrons, then proton comes. NP reaction. Okay. For example, oxygen 16 you take. Oxygen 16 plus fast neutron, oxygen 17 it will form. It will undergo a beta decay, negative beta decay. Not beta decay, I'm sorry. Ultimately what we are calling proton comes out. Proton comes out. So this is oxygen 16 plus neutron, oxygen 17. One proton comes out. Oxygen atomic number decreases. So it will become N16. N16. So O16 converted into N16. So this reaction is taking place only with the fast neutrons. This is NP reaction. Apart from proton is coming out, N16 problem is N16 is not a stable nuclide. N16 is in excited state. So it will emit the gamma ray. It will emit the gamma ray of energy 6 mega electron volt. Okay. Actually N16 what happens? It will undergo beta decay. Beta decay accompanied by a gamma decay. So N16 produced and it is emitting a gamma ray of energy 6 mega electron volt. The half-life is order of 7 seconds. 7 seconds. So most of the this reactions happens where the moderator may be air or water. It may be H2O or D2O. Air also, because air also contains oxygen, and H2O also contains oxygen, D2O also contains oxygen. So if moderator is among this O16 interacts with fast neutron, N16 forms N16 plus proton, okay, and N16 is unstable, it emits undergo a beta decay and it will emit a gamma ray of energy 6 mega electron volt. Okay, then what happens if it's further this fast neutron interacting with some other elements? One is NP reaction happen, and 2N also happens. One neutron will go, two neutrons will come out, and N3N also, one neutron will go and three neutrons will come out. This is depending on what energy of the neutron. So NP reaction, if energy is more than around 1 mega electron volt, if energy of the neutron is more than 1 mega electron volt, NP reaction is taking place. If energy of the neutron is near to 10 mega electron volt, N2N, one neutron is going, two neutrons are coming out. Okay. If it is more than 10 mega electron volt, one neutron will go, three neutrons will come out. One neutron will go, two neutrons, one proton also will come out. So the higher the energy of the neutrons, the higher the nucleons are coming out. You are following, no? Okay. Okay. O16 plus neutron, N16 plus proton. Okay. This is NP reaction. This N16 also unstable. It will undergo negative beta decay. This N16 will become O16. This O16 is unstable. It is in excited state. This O16 emits the gamma ray. The energy is 6 mega electron volt. Okay. Ultimately, in the NP reaction, what happens? Oxygen 16 interacted with fast neutron and N16 plus proton. NP reaction over. This N16 is further unstable. N16 undergone beta decay, negative beta decay. Again it formed O16, which is unstable, that is emitted a gamma ray of energy 6 mega electron volt. Okay? Now what we will discuss, Energy of the neutron, if it is more than 1 mega electron volt, NP reaction and N alpha reactions are taking place. Okay. So another example also we can discuss, uranium 232. It is not exist in the nature, but how it formed? Uranium 232. From the thorium 232, if it is interacting with the fast neutron maybe order of 10 mega electron volt energy, thorium 232 plus neutron, it will become thorium 233, undergo beta decay, protactinium it will form. And protactinium undergo beta decay, uranium 233 forms. This is general reaction. It may be whatever be the energy of the neutron, this is general reaction. Specific to the energy of the neutron, now we will concentrate. Before I told 10 mega electron, not on 10 mega electron volt. Any neutron interacting with the thorium, this is a decay series. Thorium 232 plus neutron, thorium 233 undergo beta decay, protactinium 233 undergo beta decay, uranium 233. Uranium 233 is formed. Okay. Now we are focusing uranium 232. How uranium 232 forms? This thorium 232 interacting with high energy neutron, maybe around 10 mega electron volt. Thorium 232 plus neutron gives rise to thorium 232 plus 2 neutrons. So what does it mean? So thorium taken one fast neutron and it is given 2 neutrons out. Thorium 232 plus neutron. What happened? 2 neutron coming means what happens? 231 ho jayega na? So this is not suitable example actually. The suitable example is like this. First thing, thorium 232 plus neutron, thorium 233 ban gaya. Okay. This thorium 233 undergone beta decay, protactinium 233 ban gaya. Protactinium 233. Now this protactinium also interact with a neutron, 10 MeV neutron. Okay. This protactinium 233 plus neutron gives rise protactinium 232 plus 2 neutrons. Protactinium 233 plus neutron equal to protactinium 232 plus 2 neutrons. This is N comma 2N reaction. One neutron entered, 2 neutrons came out. So protactinium 233 plus neutron 234 minus 2 neutrons 232. Now protactinium 232 formed. Okay. This protactinium 232 undergo beta decay, uranium 232 forms. This is the one of the way how uranium 232 forms. This is one of the important question. You should know this. Okay. Another way, thermal neutron may be absorbed, thorium 232. Thorium 232 plus neutron, thorium 233 undergo beta decay, protactinium 233 undergo beta decay, uranium 233. Now uranium 233 is ready. That also interact with 10 MeV neutron. Uranium 233 plus neutron equal to uranium 232 plus 2 neutrons. Okay, 233 plus 1, 234 minus 2 neutrons, 232. This way also uranium 232 forms. Okay. Very beginning also, if you consider thorium 232 plus neutron gives rise thorium 233 minus 2, thorium 231. Thorium 231 undergo beta decay, protactinium 231. Protactinium 231 absorb the neutron, protactinium 232 it will become. Okay. This protactin 232 undergo beta decay, uranium 232 forms. So these are the different ways. Means the fast neutron, the 10 MeV neutron may be directly interact with thorium. It may be directly interact with protactinium. It may be directly interacting with uranium 233 also. These are the ways we can produce uranium 232. Uranium 232. What is so special about it? Because the U232 undergo a decay series, finally one thallium 208 forms. Ultimately, one final product, it will emit high energetic gamma ray. High energetic gamma ray for shielding, it is very difficult. So that is the reason it is like hazardous. To keeping that in the industry also, it is hazardous. That is why it is concerned. Okay. So this part is clear, it seems. Next topic we will go, that will be inelastic scattering. This already I told in the previous classes also. The interaction of the neutron with moderate mass number or high mass number, it may be captured or it may be scattered. Captured, it may emit a gamma ray. Captured, it may undergo fission. Scattering means it may undergo elastic scattering, it may undergo inelastic scattering. It is same repeating only. Inelastic scattering means the kinetic energy not consumed. Neutron enter into the nucleus and that nucleus will be in excited state and it will emit a neutron with less energy. Suppose 2 MeV went inside, 1 MeV came out. Remaining 1 MeV energy is increased this internal energy. So ultimately, the inelastic collision, the kinetic energy is not conserved, but the momentum is always conserved. Okay, and this excitation energy, sorry, excitation energy for high atomic mass number, very less, order of around 0.1 MeV, not very less, but compared to with low atomic number, that is less only. The excitation energy for high atomic mass number around 0.1 MeV, 1 MeV. So with the neutron of energy more than this, the energy of the neutron must be more than 0.1 MeV, then only it will undergo inelastic scattering. Okay. Inelastic scattering, the minimum energy of the neutron, it must be equal or more than excitation state of the target nucleus. Okay, then only it will undergo inelastic scattering. If it is less than that, what happens? Obviously it cannot undergo inelastic scattering. Okay, if you take low atomic number atoms, the excitation energy is much higher. Okay, even for hydrogen there is no excitation energy. Hydrogen contains only one proton, no? If you take the hydrogen, there is no excitation state. Means the neutron interacting with the hydrogen, it will never undergo inelastic scattering. Because the nucleus contains only one proton, so there is no excitation state for that. So similarly, if you take another low atomic number like oxygen, the excitation state energy is around 6 mega electron volt, 6 MeV. So that's why I told, no, if atomic number is smaller, the excitation state energy is higher. Okay, so this is basically what is inelastic scattering. Inelastic scattering, ultimately some of energy of the neutron is given to the nucleus and nucleus will be in excited state and neutron will come out with less energy. That is inelastic scattering. Kinetic energy is not conserved. Momentum always conserves. Another is elastic scattering. Elastic scattering is kinetic energy also conserves and momentum also conserves. So in this, in elastic scattering, there are two types actually. Elastic scattering, potential scattering, another is resonance scattering. What is meant by a potential scattering? Potential scattering means neutron interacting with the target nucleus and kinetic energy and momentum exchange takes place. And kinetic energy also conserves and momentum also conserves. But this neutron will never enter into the nucleus. It means there is no compound nucleus formation takes place. The potential scattering happens with low atomic number target nucleus when the neutron energy order of a few mega electron volt. So simple sentence you remember, in potential scattering, this is related to elastic scattering only. Elastic scattering, there are two types. One is potential scattering, in which compound nucleus will not form. Neutron will come and hit and go away. Another one is resonance scattering or compound scattering, you can say. In resonance scattering, the neutron entered into the nucleus, compound nucleus formed, after that neutron expelled out. The neutron energy may be lower or higher. Finally, the kinetic energy conserves. Okay? Resonance scattering, the neutron entering into the nucleus, compound nucleus forms, it expels the neutron out with different energy, but this nucleus is still in the ground state. There is no excited state, there is no excitation takes place in this scattering. That is why this is elastic scattering. Okay? So now clearly you understood ultimately what is happening. The fission reaction is taking place, neutrons are produced, immediately they will interact with the surrounding atoms. The high energy neutrons, no fast neutrons. So high energy, no, first it will undergo inelastic scattering, because high energy, the energy is sufficient to create an excitation state in the surrounding atoms. After undergoing inelastic scattering, the energy of the neutrons comes down and it will go for elastic scattering. After undergoing elastic scattering, the energy of the neutron is sharing. Finally, energy of the neutron is coming down. It will enter. It will interact with moderator atoms also, low atomic number. Elastic scattering only takes place. Ultimately, the energy of the neutron is decreasing. Finally, it will be equal to the temperature of the neutron will be equal to the temperature of the medium, like moderator is a medium. So once the temperature of the neutron, the energy of the neutron, whatever you call, is equal to the energy of the medium, moderator, it may be heavy water, light water, or beryllium or graphite. After that also collision takes place, but there is no net exchange of energy among them. That's what actually happening after fission takes place. The neutrons are coming out, undergoing inelastic scattering, next elastic scattering. Finally, they will be equal to the moderator environment temperature attains. Okay, this is clear, it seems. After that, one more topic we will discuss, that is cross section. The beauty of the cross section is, of course, it is a imaginary thing. Okay, cross section means what? Simply cross section area. If you take a book, this, if you cut this, this is a cross section. It looks like this is a cross section area. Okay, cross section area. So why we need this cross section? Why we have to discuss in the neutron interaction with this? Ultimately, the neutrons are coming and interacting with the medium. Medium contains the atoms like uranium-235, uranium-238, plutonium, and different atoms. When neutron is coming, entering into a material, suppose this is a material. You take this. This is a material. This consists of all uranium atoms. Now neutrons are coming. One beam is coming. Like a tube. You take a small tube. In the tube, water is coming. No, like that, neutron beam is coming and falling on this area. So this area only, the atoms interact with the neutrons. The interaction may be various types. In the interaction, radiative capture also takes place, fission also takes place, scattering also takes place. So depending on energy of the neutron and what type of atom is there, depending on energy of the neutron and type of the target, this interaction changes. Interaction like scattering or capture. Okay. So this cross section area, why we are focusing? To find out the probability of a reaction takes place or interaction takes place, and how that probability changes with energy. To discuss that, we need a cross section. Okay. So the basic, if you go, the fundamental, very small uranium atom you take. Uranium atom is a spherical shape, spherical atom. Suppose this is a uranium atom. Suppose neutron is coming like this, it is falling in this, it will interact. Suppose neutron is coming like this, it is not interacted, it went out. This neutron is not at all seen, this fellow. So this, if it is going like this also not interacting, going like this also not interacting. It should be within this. The neutron should come and fall within this area, within this cross section area. So this is the probability. Higher the cross section area, higher the probability for that reaction. So ultimately, atom nucleus size only matter. The nucleus size is approximately 10 to the power of minus 15 meter. So if you take the area, take a sphere and put in light, shadow of the sphere is circle, no? Shadow of the sphere is circle, no? Circle area is pi r square. So r square, radius square. The radius size is approximately 10 to the power minus 15 meter, I told, no? 10 to the power minus pi r square, 10 to the power minus 15 whole square, 10 to the power minus 30. So if you take a range 10 to the power minus 26 meter square to 10 to the power minus 30 meter square. If you take small atom beryllium and uranium, the size may varies like this, 10 to the area, cross section area I am telling. The area 10 to the power minus area will be higher obviously for uranium, 10 to the power minus 26 to 10 to the power minus 30. So between this, I will take one definite number, 10 to the power minus 28 meter square. Cross section area, no, that's why meter square. So 10 to the power of minus 28 meter square, I am calling barn, B-A-R-N. 1 barn equal to 10 to the power of minus 28 meter square. Why I need this? Because to express the cross section in a fundamental unit, just like 1 kg, 2 kg, 3 kg, 4 kg, you will tell, no? So 1 barn, 2 barn, 540 barn, 340 barn, 3000 barn, 44,000 barn, 3,600 barn, 3 lakhs barn. This barn is unit of cross section. That will decide that reaction probability, high or low. Higher the cross section, higher the probability. So there are different cross section. Fission reaction के लिए cross section is there. Capture cross section is there. Scattering cross section is there. So we are telling this information in terms of cross section. That is why we need to know a fundamental unit type as a cross sectional area, that is a barn. 1 barn equal to 10 to the power of minus 28 meter square. Okay. With this, today we will close this class. Thanks for watching this video. Please subscribe my channel if you did it and share this video to other friends. Thanks for watching. Till next video. Bye bye.